Before getting to the scientific part of this presentation, we would like to begin with a brief demonstration of the controversy raging in the media regarding the impacts of the fracking process on the environment and surface water aquifers, in addition to the seismic effects induced by fracking. How to reduce methane emissions from the oil and gas industry across North America.
But first, natural gas is often considered a cleaner fuel than coal. It emits about half as much carbon dioxide, but the main component in natural gas is another greenhouse gas, methane.
Methane is the primary component of natural gas. It's also a greenhouse gas. Like carbon dioxide, it traps energy in the atmosphere, and according to the Environmental Protection Agency, contributes to climate change. CO2 is far more prevalent, but methane is much more potent.
Methane is about 25 times more potent a greenhouse gas on a 100-year horizon than CO2.
Earth's methane emissions are rising and we don't know why. Methane levels are increasing and scientists aren't sure why.
Maybe get the other one of the spot. Unbelievable! A river on fire! Don't let it burn the boat! Whoa! Oh! Sometimes a picture says 1,000 words. Have a look at this. The Condamine River in southwest Queensland on fire. The fracking just a kilometre away, methane coming up, and now the river is alight. Unbelievable. The most incredible thing I've seen, a tragedy in the Murray-Darling Basin. This is the future of Australia. If we do not stop the frackers who want to spread across all states and territories and do this to your community, to your environment, this is utterly unacceptable.
Final EPA study confirms fracking contaminates drinking water. Scientists struggle to explain a worrying rise in atmospheric methane. Thanks to fracking, earthquake hazards in parts of Oklahoma now comparable to California. Studies link earthquakes to fracking in the central and eastern U.S. Hydraulic fracking is behind thousands of earthquakes in the Midwest this year. Oklahoma has already had 7 earthquakes today. Texas fracking zone emits 90% more methane than EPA estimated. Oil and gas sector can bring quick climate win by tackling methane emissions. Atmospheric methane levels are going up and no one knows why.
Take a look around. It's the year 2100, and a warming planet has forever changed American cities. Here in Charleston, streets are permanently flooded, rendering parts of the city uninhabitable. Climate predictions from decades ago have come to fruition, and unfortunately, humans ignored the warnings. Warnings that are visible now. Look at Norfolk, Virginia, where today in 2019, climate change is already having real consequences. Just a steady onshore breeze and a high tide can lead to flooded roads and homes. It's even led to extensive delays in Navy ship repairs. Over the past 100 years, seas here have risen around 1.5 feet, partly because of what's happening thousands of miles away, where the warning signs are the largest, the Arctic, the fastest warming area on Earth. Changes here are drastic, undeniable, and all too real. This Greenland glacier is known as Jakobshavn. It's actually grown a bit in the past 2 years, but the long-term trend tells a different story. Take a look at this same glacier going back about 150 years ago. What you're watching is over 25 miles of ice, piled thousands of feet high. Scientists have been studying this glacier for decades, and whoa, that was a lot of ice that was there in 1851, that is no longer there today. You can clearly see the difference. And glaciers like this aren't unique. They're disappearing all over the world. It's happening now. Temperatures are rising. Ice is melting. Sea levels are accelerating upward, and it's going to get worse within our lifetime.
A new study, published in Biogeosciences, finds that shale oil and gas is behind the global rise in methane pollution over the past decade, a major source of greenhouse gas emissions. The study was able to distinguish between methane emissions from conventional versus unconventional drilling, as well as methane from other biogenic sources, such as agriculture or wetlands. The study, authored by Robert Howarth, the professor of ecology and evolutionary biology at Cornell University in the United States, concludes that shale gas production in North America over the past decade may have contributed more than half of all of the increased emissions from fossil fuels globally, and approximately one-third of the total increased emissions from all sources globally over the past decade. The study says that in addition to contributing to climate change, methane emissions lead to increased ground-level ozone levels, with significant damage to public health and agriculture. In a statement, Howard said that carbon dioxide and methane are critical greenhouse gases, but they behave quite differently in the atmosphere. Carbon dioxide emitted today will influence the climate for centuries to come, as the climate responds slowly to decreasing amounts of the gas. Unlike its slow response to carbon dioxide, the atmosphere responds quickly to changes in methane emissions. Reducing methane now can provide an instant way to slow global warming and meet the United Nations target of keeping the planet well below a 2°C average rise, he said, referring to the 2015 Paris Agreement that boosts the global response to climate change threats. Atmospheric methane levels have previously risen during the last 2 decades of the 20th century, but leveled in the first decade of 21st century. Then, atmospheric methane levels increased dramatically from 2008 to 2014, from about 570 teragrams, 570 billion tons, annually, to about 595 teragrams, due to global human-caused methane emissions in the last 11 years. This recent increase in methane is massive, Howard said. It's globally significant. It's contributed to some of the increase in global warming we've seen, and shale gas is a major player. If we can stop pouring methane into the atmosphere, it will dissipate, he said. It goes away pretty quickly, compared to carbon dioxide. It's the low-hanging fruit to slow global warming. To understand the climate dimensions of the upstream sector of oil and gas development, we in GSDCS have studied the mechanisms through which methane migrates from the shale source rocks to the environment. The mechanisms of contaminating the surface aquifers with methane and chemicals from drilling and fracking fluids, and the mechanisms of connecting the fracking and disposal wells to nearby faults causing seismic events, had been studied as well. We would like to start the scientific part with highlighting a few outstanding articles addressing the topic of natural and induced fractures. Jahoon Kim and George Moridis co-authored an article titled, Numerical Analysis of Fracture Propagation During Hydraulic Fracturing Operations in Shale Gas Systems. This article was published in the International Journal of Rock Mechanics and Mining Sciences. From this article, we have the following quote. Fisher and Warpinski analyzed fracture propagations induced by hydraulic fracturing with real geophysical field data, and concluded that the fracture propagations were limited in the vertical direction, compared with the horizontal direction. They claim that an unstable fracture propagation up to near surface is not possible because, for example, 1. The formations between the near surface and the shale gas reservoirs are not homogeneous, and 2. The horizontal total stress is higher than the vertical total stress at shallow depth, which can block the growth of the fracture along the vertical direction. Osborne et al. Investigated the methane concentrations in the drinking aquifers for the active and inactive areas of shale gas production, and found that groundwater was contaminated around the active area of the gas production, where methane possibly originated from the shale gas reservoir, based upon the isotope analysis. And from this article's conclusion, we have the following quote. From various numerical tests, hydraulic fracturing produced stable fracture propagations, supporting the argument from the real data in the previous studies, for example, no greater than 460 meters of vertical fracture propagation, inferred from microseismic signals. Durham University published a research brief, based on a review article by Richard Davies, Simon Mathias, Jennifer Moss, Steiner Hustift, and Leo Newport, titled, Hydraulic Fractures, How Far Can They Go? And published in the Marine and Petroleum Geology Journal. From this brief, we have the following quotes. Research led by Durham Energy Institute indicates that there is a less than 1% chance of a stimulated hydraulic fracture propagating upwards for more than 350 meters, and that the maximum recorded distance of such a fracture is less than 600 meters. For natural fractures, Analysis of 1170 examples from offshore Norway, West Africa and Namibia showed the maximum reported height to be 1106 meters. For thousands of stimulated hydraulic fractures in shale gas fields, the maximum reported height was 588 meters. In the What Can We Conclude section of this brief, the co-authors argue that, based on the data analyzed, natural fractures have the potential to grow upwards further than man-made ones. The co-authors also claim that the data indicate that very few stimulated hydraulic fractures propagate more than 350 meters. With drinking water aquifers typically being about 300 meters below the surface, and most fracking occurring at depths of 2 to 3 kilometers, it is extremely unlikely that a stimulated hydraulic fracture could connect the two zones. An article titled Natural Fractures in Shale, a Review and New Observations, and co-authored by Julia Gale, Stephen Laubach, John Olson, Peter Eichubel, and Andres Fall from the University of Texas at Austin is also informative in this regard. From that article, we have the following excerpts. Burial history and fracture diagenesis influence fracture attributes, and may provide more information for fracture prediction than is commonly appreciated. The role of microfractures in production from shale is currently poorly understood, yet potentially critical. We identify a need for further work in this field, and on the role of natural fractures generally. And because the kinetics of dissolution, transport, and precipitation are generally favored with an increase in temperature and a decrease in grain size, chemical-mechanical interactions between fracture growth and host rock diagenesis are most pronounced in fine-grained rocks of chemically reactive composition, and are thus generally more pronounced in shales than in sandstone at similar burial depth. And the prospects for advances in understanding of shale fractures, and thereby their effects on production, are good. Diagenetic methods allow sharper differentiation of when and why fractures formed. Another article titled, Using Structural Diagenesis to Infer the Timing of Natural Fractures in the Marcellus Shale, co-authored by Laura Palmer, Julia Gale, Peter Eichubel, Andres Fall, and Stephen Laubach. Bureau of Economic Geology, University of Texas at Austin. This article concludes that the natural fractures in shale must have formed during burial rather than uplift. These four articles summarize in analyses and statistics the geomechanics and the clay's chemistry points of view regarding the generation of shale fractures. These articles demonstrate the crucial role of clay's chemistry in creating such fractures. In GSDCS, our studies focused on the authogenic transformations and changes in clay structures and masses. These changes result from the chemical reactions of specific clays with specific components of improperly designed water-based drilling and fracking fluids, creating shale fractures. The new technique of drilling horizontally in the shale source rocks for thousands of feet, with the applicable circulation rates of water-based drilling fluids with specific components, gives a very high kinetics of such chemical reactions. Such chemical reactions last for a very long time, compared with the conventional drilling technique of vertically penetrating few tens of feet or even less of the shale source rocks. On top of that, pumping huge volumes of water-based fracking fluids with specific components in the shale source rocks is adding another huge scale of such chemical reactions and authogenic clays transformations. As demonstrated in the first article, the phenomenal relation between horizontal drilling and unconventional completion techniques with the methane migration into the atmosphere and into the subsurface water aquifers is widely addressed. Geologically, clay minerals exist abundantly in the earth crust. Our studies show that the induced fractures starts in shale source rocks and extend horizontally, diagonally and vertically, wherever there are clay minerals in the overlying formations. So, the existence of specific clay minerals in the shale source rocks and the overlying formations up to the surface, the utilization of specific drilling and fracking products, the duration of drilling and circulation, and pumping of huge volumes of fracking fluids into the shale horizontal sections, are factors determining how far these fractures can go, and in which direction, even for thousands of feet. This phenomenon physically far exceeds the Wells integrity criteria, and these chemically induced fractures far exceed the lengths of fractures mechanically induced by the fracking process itself, since these mechanically induced fractures are limited in lengths as demonstrated earlier in the first two articles. To practically prove this approach, we just need specific data from any case of methane migration into the atmosphere or subsurface water aquifers, any case of subsurface water contamination, and any case of seismicity related to unconventional oil and gas upstream activity. We will highly appreciate any cooperation from the academic and the industrial sectors to get this mission accomplished. Let's work together, hand in hand, and shoulder to shoulder, to save our Earth and give our next generations a better life on a healthier planet.
Today I'm appealing for leadership from politicians, from business and scientists, and from the public everywhere. We have the tools to make our actions effective. What we still lack, even after the Paris Agreement, is the leadership and the ambition to do what is needed. And what makes all of this even more disturbing is that we were warned. Scientists have been telling us for decades, over and over again. And far too many leaders have refused to listen. And far too few have acted with the vision the science demands. And we see the results. In some situations, they are approaching scientists' worst-case scenarios. The world's richest nations are the most responsible for the climate crisis, yet the effects are being felt first and worst by the poorest nations and the most vulnerable peoples and communities. Existing technologies are waiting to come online: cleaner fuels, alternative building materials, better batteries, and advances in farming and land use. And these and other innovations can have a major role in reducing greenhouse gas emissions so we can hit the Paris targets and inject the great ambition that is so urgently needed. Let us use the next year for transformational decisions in boardrooms, executive suites, and parliaments across the world. Let us raise our sights, build coalitions, and make our leaders listen. There is no more time to waste. As the ferocity of this summer's wildfires and heat waves shows, the world is changing before our eyes. We are careering towards the edge of the abyss. It is not too late to shift course, but every day that passes means the world eats up a little more and the cost of our inaction mounts. Every day we fail to act is a day that we step a little closer towards a fate that none of us want. A fate that will resonate through generations in the damage done to humankind and life on Earth. Our fate is in our hands. The world is counting on all of us to rise to the challenge before it is too late. I count on you all.